everyone. Today I will present our work titled Modeling and Learning Multiple Hypotheses for Monocular 3D Object Detection, which has been accepted to WACV 2026. This work addresses a fundamental limitation of monocular 3D object detection, the inherent ambiguity of depth estimation from a single RGB image. 3D object detection aims to predict 3D bounding boxes from just one image. While it is cost-effective and widely deployable, its core challenge lies in depth estimation. Because we only observe 2D projections, depth is inherently ambiguous. In fact, prior work shows that simply replacing predicted depth with ground truth depth improves performance by more than 20% MAP on Kitty. This clearly tells us that depth uncertainty is a major bottleneck. From a geometric perspective, monocular 3D detection is an ill-posed inverse problem. A single 2D observation can correspond to multiple valid 3D configurations. For example, similar 2D projections may arise from objects located at different depths. However, most existing methods regress to a single point prediction, producing only one 3D bounding box per object. As a result, the model often converges to an implausible mean solution, failing to capture the multimodal nature of the problem. To address this issue, we propose MonoMH, a multi-hypothesis framework for monocular 3D object detection. The key idea is simple. Instead of predicting a single 3D box, we explicitly model and learn multiple plausible hypotheses, especially for uncertain objects under occlusion, truncation, or perspective ambiguity. This naturally raises three research questions. How do we generate diverse hypotheses? How do we learn them from single ground truth supervision? And how do we use them effectively during inference? This slide shows the overall framework of MonoMH. At a high level, we follow a standard 2D to 3D detection pipeline, but introduce three new components: multi-hypothesis prediction, learning, and filtering. Let me briefly explain each of them. First, how do we generate multiple hypotheses? We divide the 2D ROI feature map into spatial windows. Each window predicts one 3D hypothesis. This design leverages spatial diversity within the object region. For example, different parts of a car, such as the front or the wheels, may provide distinct depth cues. Importantly, we allow independent localization and confidence for each hypothesis while sharing size and orientation to maintain stability. Second, how do we learn them? We draw inspiration from the best of many loss, which supervises only the hypothesis closest to the ground truth. However, supervising only one hypothesis restricts gradient flow and may limit learning effectiveness. To address this, we propose a soft best of many loss, which relaxes the supervision and allows multiple hypotheses to receive gradients. This improves training stability and encourages meaningful diversity. Finally, how do we use multiple hypotheses? Naively generating multiple boxes for every object would increase false positives. Therefore, we introduce hypothesis filtering. For confident objects, we keep only the best hypothesis. For uncertain objects, we retain multiple plausible ones. We also remove outliers using confidence-aware filtering. This allows us to improve robustness without sacrificing precision. We evaluate our method on the Kitty 3D detection benchmark using AP3D. On the official test server, MonoMH outperforms previous state-of-the-art methods across categories and difficulty levels. This demonstrates that explicitly modeling multimodality leads to consistent and reliable performance gains. Here we show qualitative comparisons. Compared to single-point baselines, MonoMH produces more accurate and geometrically consistent 3D boxes, particularly in challenging cases such as occlusion and truncation. To conclude, monocular 3D detection is inherently multimodal. Existing single-point approaches ignore this ambiguity. We propose a principled multi-hypothesis modeling and learning framework that explicitly captures multiple plausible 3D configurations. Our method improves robustness and detection performance by better handling depth uncertainty. Thank you for your attention.